So we're looking at applications of quadratic functions. This is like, I think this is kind of cool that you can actually do some things now. We know enough to where we don't have to be too contrived. We can actually solve some questions that are, you know, reasonably you could think are of some importance, right? So quick reminder, if we start with a quadratic function in standard form, we can find the coordinates of the vertex pretty easily, right? We have this one little formula we have to remember. H equals negative b over 2a, and k we get by just feeding that value into the function, right? Like we always do if we want to find a y value. So k is just f of h. And remember, a, b, and c are just the coefficients that show up in standard form, ax squared plus bx plus c. We also know, of course, that if a is positive for a parabola, what does that mean about the parabola? Opens up. Good. So the vertex would then be a minimum, right? Be the minimum value of the function. If a is negative, it opens down. The vertex would be the maximum value of the function. Okay? All right, so let's look at a couple interesting applications here. So let's say, for example, and this is a reasonable thing to want to be able to do, if you want to fabricate a rain gutter out of a piece of aluminum, let's say, okay, you're going to make a channel. You're expecting big thunderstorms. You need to be able to evacuate that water. So you're starting with an 18-inch wide sheet of aluminum, and we're just going to bend the edges up to create a rectangular channel that the water is going to flow through. Everybody get what we're doing here? So the water's here's the water sloshing around, coming down towards us down the aluminum gutter. Okay, make sense? Okay. All right, so we want to try to determine where would we make the bends to be able to maximize the flow. To maximize the flow, we would just want to maximize the cross-sectional area of the gutter. Everybody agree? Okay. Okay, so how are we going to do that? Any ideas? Okay, so we're going to have to bend up the two sides. So let's say we're going to make the bends like right here and like right there and right there, let's say, right? We're going to bend those up to create the sides of the gutter. Okay, if we're going to be able to do this mathematically, we need the math gods to help us here. We got to be able to come up with an equation, though, right? We have to be able to come up with some kind of a relationship that we can deal with mathematically. So what could my variable be here? What's the thing that I vary about this problem? What do you think, Aurora? Okay, so how big am I? How much am I bending up, right? So we could call this distance right here, for example, from there over to there. We'll call that x, and that's x. Okay, what does that leave us in the middle then? Well, I mean, we could, but we'd rather if we can avoid another variable. Let's see if we can. No, if I'm going to bend these up, how much is left in the middle? How wide is it going to be? 18 minus 2x, isn't it? Right, because I'm taking the whole 18 and I'm just subtracting away 2x when I bend those up. Does everybody agree? Okay, so then over here on my figure, this looks like x, and this looks like 18 minus 2x. Those are the dimensions of my channel. Okay, give me thumbs on that. Everybody with me? That all makes sense? Okay. Okay. Good. All right, so we want to maximize the cross-sectional area, so we need to have some kind of an area equation here, right? Okay, well, what's the cross-sectional area? Oh, I don't think you are. That's no big deal. Yeah, how do you calculate the area of a rectangle?
18 minus 2x times x.
Yeah, you just multiply length times width, don't you? Right? So x times 18 minus 2x is the area. Everybody agree? Okay, give me 1 to 5. Is everybody with me? Can you picture this okay? What we're doing here? Right? Okay, so I could make it a little bit like if I did this, would this make it easier to picture like if this really is it's a long gutter that looks like that, right? And there's water flowing down this, right? And we've got this and the water's coming flowing down the gutter. See what I'm saying? Everybody with me?
Looks like you just took a picture. You sliced the gutter in half with water just frozen in place.
Yeah, that's kind of what it is. Exactly. I just sliced through the gutter. Right. Okay.
Okay. I'm sorry.
Right? Everybody get that? Okay. So then this is my area function for the cross-sectional area. I could write this as a function of x, right? Because the input variable is x in this case, and I'm calculating area, which is the output. Okay. What if I were to distribute the x? That would put this into a form that we're familiar with. I'm going to put, when I distribute the x, what am I going to get? No, what's x times 2x squared? Okay, so let's put the x squared term first and write it like that. What's that look like? What kind of function is that? That's a quadratic function in standard form, isn't it? Okay. So we should be able to figure out then. Now, you always want to be thinking about this stuff, and this is such an important skill in math. People, like in calculus, I harp on this all the time. You always want to try to think about what a graph might look like. You don't always have to have an exact version of the graph, but in your mind, you want to do a sketch at least and think about basically what's that going to look like. Well, if I graph this, first of all, what are going to be the axes in the coordinate plane that I'm going to use? What goes on the vertical axis for this function? What is it? A of x. Yeah, it's always the output goes on the vertical axis, right? So this is going to be a of x. What's the input variable? Because that's what goes on the horizontal axis, x. So we're just graphing, a of x versus x, right? Just like we'd normally graph y versus x or f of x versus x. What's the shape of this graph going to be? Parabola that opens down because a is negative. Everybody agree? Okay, so we're going to get something like this over here, right? So then the vertex is going to be the maximum for area, isn't it? Everybody get that? So if we've got a quadratic function and we're trying to find a maximum or a minimum, a lot of times we can answer those questions by simply identifying the coordinates of the vertex, right? So we just need to know what are the coordinates of the vertex. Well, we can calculate those. That's no big deal. We have a formula for that. How do I calculate? Because really this is just HK, isn't it? See what I'm saying? Okay, so what's our formula for H? Okay, so if I plug in my values then, what's negative B? Negative 18. What's 2 times A? Negative 4. So negative 18 over negative 4 is positive 9 over 2, which we'll just write as a decimal as 4.5. Okay. So that tells me that the x coordinate is 4.5. Does it even ask for, what's the question ask for? Just wants the depth of the gutter. It doesn't even want to know what the cross-sectional area is. We just want to know, how could I build the most efficient gutter? Well, what's the depth of the gutter going to be then? 4.5. It's x. We solved for the x coordinate of the vertex. Everybody get that?
Yeah.
Okay.
4.5.
Right? Does everybody make that connection? Yeah. Right. X is, by definition, x is the depth of the gutter. And so what we've got here is an area function that's giving us the area of the different gutters that we could build depending on where we, how much we bend up for the edge of the gutter. If I bend up an amount that's less than 4.5, I'm going to get a cross-sectional area that's smaller than that maximum. Or if I pick a value greater than 4.5, I'm going to get a cross-sectional area less than my maximum, right? So we don't even really need to know what K is. We just need to know what X is, and that answers the question. What is, determine the depth of the gutter that will maximize the cross-sectional area? 4.5 inches. There it is. We got it, right? That's pretty cool. We could do that easily, right? Let's try another one. Okay, how about this? The cost in millions of dollars for a company to manufacture X thousand automobiles is given by the function C of X equals 4x squared minus 24x plus 72. Okay. Find the number of automobiles that must be produced to minimize the cost. Okay. Did I talk to you guys about like the math jobs where you do this stuff the other day? A little bit. Yeah. I mean, so here's another example of like this is a really simple entry level example of the kinds of things that professional mathematicians would do to try to, when they work for these companies, to try to do something like minimize the cost of producing automobiles, right? It's more complicated than this, but this is a model that might not be a bad approximation. Okay, so if we've taken some data and we've done some curve fitting, we used regression and we came up with that cost function, let's say. Okay, so what do we do then? Well, if we want to minimize cost, think about this in terms of a graph. So for our function, what's the quantity that we're going to attach to the vertical axis? C of x. That's the output variable. Input variable, x. X, remember, x is the number of automobiles in thousands that's going to produce an output cost of C of x in millions. Okay? All right, well, all we've got to do is just figure out, based on our function that's in standard form, right? It's a quadratic function in standard form. What are the values of A, B, and C? Negative 24. We don't even care about C, right? We just need A and B. And so H is negative B over 2A. What's negative B? 24. 2A. So if we were to graph this function, this is a parabola, right? It's quadratic. It's a parabola that opens up, right? And so the coordinates of the vertex are going to be 3. Who cares, right? All we needed to know was what's going to be the input value of x that's going to minimize cost. 3, right? So 3,000 cars minimizes production costs. Okay, good. Okay, one more. So what about this? A person plans to use 2,200 feet of fencing to enclose a rectangular garden. What dimensions of the rectangle would give the maximum area? Okay. So, and then we want to know what is that area? Okay. So this time they're asking 2 questions. Okay. So first of all, let's draw a picture. It's always good when you're dealing with like geometric stuff. Draw a picture, and it's easier to just fill in the pieces on the picture. So here's our rectangle. Let's say, just so we can keep track of this, there are easier variables to use. Let's use x's and y's, how about? And we can turn those into w's and l's at the end if we want to, right? Okay, so let's just say x is going to be the length and y is going to be the width. Okay? This time it looks like we need 2 variables, doesn't it? Right? Okay, so what does the first equation tell us up here? Okay, so that's perimeter, isn't it? Okay, so what are we going to get for perimeter here then? What's our perimeter equation going to be with x's and y's? 2x plus 2y equals perimeter, which is 220. Okay. All right, so what are we trying to find? Area. We're trying to maximize area, right? So we're going to need some area function. How do you calculate the area of a rectangle? X times y. Okay, so the problem here is, like, look, our output area is a function of 2 input variables. That's not good. So we need to make a substitution. That's why we have this other equation, though, right? We've got a system of 2 equations in 2 unknowns. Remember doing stuff like this, right? We dealt with linear systems. This is just the next step. This is a nonlinear system. The green equation is a line, but the whatever that is, the pink one is not, right? So it's still just a system, just not a linear system, okay? So what do we do? How are we going to solve this thing? How do we solve a system? Okay, we could solve for a variable in this equation and substitute, right? So why don't we solve for y? So we get 2y equals 220 minus 220 minus 2x. Next step? Divide by 2. Okay, so if I divide by 2, I get y equals, I got to divide everything by 2. 220 divided by 2 is 110. 2x divided by 2 is x. Okay, so I get the substitution equation, y equals 110 minus x. Okay, well, I can make that substitution right there. Okay, so then I end up with a equals x times 110 minus x, right? Okay, which is the same thing if I distribute my x. That's 110x minus x squared. Let's write that as a of x. Let's write it in standard form, so I'm putting the x squared term first. Okay, that's just a quadratic function in standard form, agreed? Okay, so what's the value of h? What's negative b? Divided by 2a, that's just negative 2, right? So what do I get, 55? Okay, so everybody agree? I mean, I'm just doing just a little arithmetic, right? So now if we were going to think about this in terms of a graph, we've got area is our output variable, x is our input variable. Is this parabola opening up or down? Down. A is negative, right? Okay. So it's opening down. Oh, what did I do?
You went to the next page. There you go.
Okay. So we just need the coordinates of the vertex, right? Well, we know the x coordinate is 55. To find the y coordinate, we'll just plug that into our function. A of 55 equals negative 55 squared plus 110 times 55. So that's 5,500 plus 57. So it's going to be 6. Is that going to be, God, so 30, 25? Is that's what that is, right? I get 6,050.
Calculator?
His brain is
Okay, so then that's K, isn't it? Right? That's K. What did we just do? No, because look what we're going to do. Here's, 110 is twice 55. So we can just do 110 times 55 and then cut it in half. Right? See, that's all we're doing. Right? You get that? And so what's that doing then? That's just giving us, what's that do? That gives us 5,500 plus 550, which is 6,050. Cut in half is 3,025. Okay. So we know what K is. K is 3,025. And so the width then is 55, right? Units would be feet, right? The length, we have to figure out what the length is. Well, we'll go back and calculate y. So 110 minus 55 is 55. Okay. Feet. Is that surprising? Think about that now. You probably could have told me what the shape was going to be, couldn't you? If I gave you, well, a square is a rectangle, right? So you could have probably told me that. If I had said, if I gave you a certain amount of fencing and said enclose the most area you can, what shape would you make? You'd make a square, wouldn't you? That's gonna be the most efficient way to enclose area. And so the maximum area is, there's our 3,025. What are the units going to be?
Feet squared.
Feet squared or square feet.
Square feet.
Okay.
Same difference.
What do you think? I mean, pretty impressive. We can do that, right? Okay. All right.